Right now, Earth's magnetic North Pole is drifting at approximately 40 kilometers per year according to NOAA's World Magnetic Model 2025, representing the most significant deceleration in recorded history. This behavior matches patterns described in a partially declassified document from 1966 that theorizes how previous civilizations were destroyed by catastrophic pole shifts. For nearly 60 years, the government kept most of this information classified, releasing only 57 pages of the original 284-page manuscript. With 2025 data showing unprecedented magnetic field changes, increasing global seismic activity, and climate patterns that include unusual jet stream behavior and extreme weather events, scientists are questioning whether we're witnessing early warning signs of the next catastrophic reset. The author of that classified document wasn't just any researcher. The CIA's hidden Doomsday Files. Dr. Chan Thomas worked as an engineer at McDonnell Douglas, one of America's largest aerospace contractors, when he published the Adam and Eve story in 1966. Thomas had spent years analyzing geological data, studying ancient flood myths, and examining patterns in Earth's magnetic field behavior. His conclusions were concerning enough that the CIA acquired his manuscript and kept it in their files for nearly 6 decades. The government's response to Thomas's work reveals something important about the content. Instead of simply ignoring what they could have dismissed as French science, intelligence agencies took the unusual step of maintaining his document in their personnel security files. This classification lasted for nearly 6 decades, and when the CIA finally released portions of the document in 2013, they provided only 57 pages. Of the original 284 pages, only these 57 contained actual content, while the rest were blank pages. The agency described the released pages as sanitized, meaning they had been carefully edited to remove sensitive information. Thomas's background as a McDonnell Douglas engineer gave him access to geological surveys, magnetic field measurements, and seismic data that weren't widely available to civilian researchers. His conclusions about catastrophic events came from analyzing data sets that painted a picture of Earth's magnetic and geological behavior that differed from mainstream scientific understanding at the time. The Adam and Eve story presents Thomas's theory that Earth experiences catastrophic events involving rapid shifts in the planet's magnetic poles, followed by massive crustal displacement that causes worldwide destruction. Thomas argued that these shifts happen quickly and result in the complete collapse of existing civilizations. He claimed that humanity has experienced these resets multiple times throughout history, with each advanced civilization being destroyed and the survivors forced to rebuild from primitive conditions. However, his specific claims about precise cyclical timing lack peer-reviewed scientific support and remain outside mainstream geophysical consensus. The government's acquisition of Thomas's manuscript created questions that persist today. While mainstream scientists dismiss theories about rapid pole shifts as lacking evidence, the CIA's interest suggests these theories contained information worth examining. This has led researchers to question what the unreleased portions of Thomas's manuscript might reveal. Some speculate that the classified pages include detailed geographic analysis, specific calculations based on magnetic field measurements, or connections to other research projects studying similar phenomena. Thomas had access to data from various installations, including magnetic observatories and seismic monitoring stations. His conclusions were based on measurements that weren't available to academic researchers. The portions of his work that remain in government files likely contain analysis of this restricted data, along with predictions about future magnetic behavior that officials considered worth preserving. Archaeological discoveries have added some context to aspects of Thomas's work that were once completely dismissed. Evidence shows that multiple advanced civilizations existed before recorded history, many of which disappeared suddenly under circumstances that remain unclear. Geological surveys have identified rapid climate changes and massive flooding events that occurred throughout human history. These findings have led some researchers to reconsider whether certain aspects of Thomas's theories deserve scientific attention, even if his specific cyclical predictions lack supporting evidence. The intelligence community's interest in Thomas's work extended beyond simple curiosity about geological theories. Documents released through Freedom of Information Act requests show that government agencies establish research programs to study crustal displacement mechanics, magnetic field instability, and catastrophic risk assessment. These programs were initiated in the late 1960s, and some continue operating today under different classifications. Thomas's position also gave him access to international research collaborations that weren't publicly acknowledged. Scientists from various countries were sharing data about magnetic anomalies, seismic patterns, and atmospheric changes that revealed concerning patterns of geological activity. This international cooperation suggests that Thomas's conclusions incorporated global datasets that revealed worldwide patterns worth monitoring. The timing of the CIA's acquisition is significant because it occurred during a period when government agencies were becoming increasingly concerned about potential threats to national security. The Cold War had created an environment where any information that could cause public disruption was considered sensitive. Thomas's predictions about catastrophic events would certainly qualify as potentially concerning information, especially if his calculations suggested that major changes were approaching within decades. The continued maintenance of Thomas's files also suggests that he included practical information about surviving catastrophic events. The released portions of his manuscript focused primarily on theoretical discussions of past catastrophes and general descriptions of cyclical processes. The unreleased sections likely contain specific geographic analysis, survival strategies, or detailed calculations that the government considers sensitive. This practical information would be exactly the type of content that intelligence agencies would want to control. Government monitoring programs established after Thomas submitted his research have tracked the types of changes he predicted would precede catastrophic events. Magnetic field measurements, seismic activity patterns, and atmospheric anomalies have all been carefully documented since the 1960s. The fact that these monitoring efforts continue today, more than 50 years after Thomas's initial work, indicates that his observations remain relevant to current government planning. Thomas's work built on earlier research by Charles Hapgood, whose theories about crustal displacement had gained support from Albert Einstein and other prominent scientists. However, Thomas went further by incorporating magnetic field data and establishing what he claimed were specific patterns for catastrophic events. His analysis of ancient flood myths, geological formations, and magnetic pole positions suggested predictable cycles, though these claims lack the peer-reviewed validation that modern science requires. The intelligence community's sustained interest in monitoring global magnetic and seismic activity suggests that Thomas's observations about planetary instability contained elements worth tracking. Whether his specific predictions prove accurate remains to be seen, but the data being collected today provides an unprecedented view of how Earth's magnetic field actually behaves during periods of rapid change. 2025's alarming magnetic anomalies. Current measurements reveal magnetic field changes that are setting new records for documented geological history. The magnetic North Pole has accelerated its movement to approximately 40 kilometers per year according to NOAA's World Magnetic Model 2025, representing a dramatic increase from the 15 kilometers per year that researchers recorded in the 1990s. The pole's path has also become erratic, shifting directions multiple times within single calendar years instead of following the predictable northwestern trajectory it maintained for decades. The geomagnetic field strength has declined approximately 9% over the last 200 years, with recent measurements showing this decline may be accelerating. Ground-based observatories and satellite magnetometers are recording data that shows this acceleration began around 2019 and has continued steadily through 2025. The European Space Agency's Swarm satellite constellation has documented field strength losses that exceed previous models for magnetic field behavior during stable periods. Navigation systems worldwide have required constant recalibration to account for these rapid changes. GPS satellites, which depend on accurate magnetic declination data for positioning calculations, now need monthly updates to their reference systems instead of the annual updates that were sufficient for decades. Aviation authorities have issued new protocols requiring pilots to verify magnetic compass readings against GPS coordinates before takeoff because magnetic declination charts are becoming obsolete within weeks of publication. Marine navigation has become particularly challenging, as ships relying on magnetic compasses are experiencing errors of several degrees that change faster than traditional navigation charts can be updated. The South Atlantic Anomaly represents one of the most concerning aspects of current magnetic field behavior. This region of weakened magnetic field strength, which allows dangerous radiation to penetrate closer to Earth's surface, has expanded by 20% since 2020. The anomaly now extends from South Africa to southern Brazil and has developed secondary weak spots that appear and disappear within months. Satellites passing through this region are experiencing increasing numbers of technical malfunctions as radiation exposure damages their electronic systems. The International Space Station has had to modify its orbit multiple times in 2025 to minimize crew exposure when passing through these weakened areas. Scientists working at magnetic observatories are reporting unprecedented readings that don't match any historical patterns in their databases. the World Magnetic Model, which provides the baseline for all global navigation systems, has required 3 emergency updates since 2020 instead of the normal 5-year revision cycle. Researchers at the British Geological Survey have documented magnetic field variations that occur over periods of days rather than the typical months or years. These rapid fluctuations are creating measurement errors in everything from smartphone compasses to military navigation systems. Thomas's 1966 predictions about magnetic field behavior preceding catastrophic events show some alignment with current observations. He described a period of accelerating magnetic pole movement followed by field strength decline that would precede crustal displacement. However, his specific claims about rapid crustal displacement lack scientific support, with most geophysicists considering such theories physically implausible without substantial evidence. The dramatic acceleration in magnetic pole movement that began in 2019 represents unprecedented behavior that scientists are working to understand through conventional geological processes. The distinction between magnetic excursions and full reversals has become critical for understanding current changes. During a magnetic excursion, the field weakens dramatically and the poles move rapidly, but the field eventually stabilizes without completely flipping. A full reversal involves the magnetic north and south poles switching positions permanently. Current data suggests Earth might be entering an excursion rather than a full reversal, but scientists acknowledge that the early stages of both processes look identical. Magnetic field models developed by the University of Rochester and other institutions show that current changes are following patterns associated with rapid magnetic transitions rather than gradual, long-term evolution. Computer simulations indicate that when magnetic field strength drops below certain thresholds, the field becomes unstable and can change configuration within decades rather than millennia. The current rate of field weakening suggests that Earth's magnetic field could reach these critical threshold levels within the next 10 to 15 years. Technology failures linked to magnetic anomalies are becoming more frequent and severe. Power grid operators report increasing numbers of transformer failures in regions experiencing rapid magnetic declination changes. The electrical grid relies on magnetic field stability for proper operation of protective systems and load balancing equipment. As magnetic conditions become more chaotic, these systems are triggering false alarms or failing to activate when needed. Satellite operators have documented a 300% increase in radiation-related malfunctions since 2020, with most failures occurring in regions where magnetic protection has weakened. Communication systems are also showing signs of magnetic field-related stress. Radio propagation patterns have become increasingly unpredictable as the ionosphere responds to changing magnetic conditions. Military communication networks that depend on specific frequency ranges are experiencing interference patterns that don't match any previous data. GPS accuracy has decreased in certain geographic regions where magnetic anomalies interfere with satellite signal processing. Scientific institutions have quietly begun intensive monitoring programs to track magnetic field changes with unprecedented precision. The National Oceanic and Atmospheric Administration has deployed additional magnetic monitoring stations across North America, focusing on regions where field strength is declining most rapidly. European and Asian research centers have established similar networks, creating a global monitoring system that provides real-time data on magnetic field fluctuations. This international coordination suggests that government agencies are taking current magnetic anomalies seriously as potential indicators of larger geological processes. Research teams studying paleomagnetic records have found that previous magnetic excursions occurred with similar patterns of accelerating change followed by rapid field transitions. Ice core samples and volcanic rock formations show evidence of magnetic field strength dropping to less than 10% of normal values during past excursions. These historical examples demonstrate that magnetic field changes can happen much faster than previously thought possible, though the geological record shows these changes occurred through natural processes rather than the catastrophic scenarios Thomas described. The mounting evidence of magnetic field instability has prompted researchers to examine whether similar rapid changes in Earth's magnetic system coincided with other significant events in human history. This investigation has led scientists to archaeological sites where recent discoveries are revealing patterns that weren't visible to previous generations of researchers. Ancient catastrophe evidence hidden in plain sight. Archaeological discoveries made between 2020 and 2025 have revealed evidence that supports aspects of Thomas's theory about cyclical catastrophes affecting human civilizations. Teams using advanced sonar mapping technology have identified underwater structures that show signs of sophisticated construction techniques, though the specific dating and extent of these discoveries remain subjects of ongoing Research and debate within the archaeological community. Excavations across multiple continents have uncovered mysterious layers of mud and sediment that appear to have been deposited rapidly over large areas. These layers contain a mixture of marine and terrestrial materials that suggest massive flooding events occurred simultaneously across different geographic regions. Archaeological sites in Peru, Turkey, and North America all show evidence of sudden burial beneath thick layers of mud that contain shells, marine organisms, and debris from different elevations mixed together. The composition of these mud layers indicates they were created by catastrophic flooding that moved material from ocean floors to mountaintops within short periods. Ground-penetrating radar surveys performed in 2025 have identified massive buried structures on every continent that show signs of sudden catastrophic burial. These structures include what appear to be foundations of large buildings, road networks, and infrastructure systems that were rapidly covered by debris flows. The burial patterns are consistent across different continents and show evidence of simultaneous destruction events that affected multiple civilizations at the same time. Radar penetration depths reveal that some structures are buried under 20 to 30 meters of sediment that appears to have been deposited rapidly rather than accumulated gradually over time. Multiple cultures share flood legends, and mainstream science links many to post-glacial meltwater pulses around 11,500 years ago, though not necessarily to global pole shifts. The Sumerian Epic of Gilgamesh, Hindu Puranas, Chinese flood myths, and Native American traditions all contain detailed descriptions of catastrophic flooding that destroys advanced societies. These stories include specific details about the sequence of events, the duration of the catastrophic period, and the geographical changes that result from the disasters. The consistency of these accounts across cultures that had no contact with each other suggests they may be describing actual historical events rather than purely mythological stories. Geological evidence supports aspects of the flood narratives by showing that rapid climate changes and massive water movements occurred at the times described in ancient texts. Ice core samples from Greenland and Antarctica contain chemical signatures indicating that major climate disruptions occurred approximately 12,000 years ago. These signatures show evidence of rapid temperature changes, altered precipitation patterns, and atmospheric composition changes that would accompany major environmental shifts. Sediment cores from ocean floors also contain layers of material that were deposited rapidly during this same time period. Archaeological evidence suggests that previous civilizations understood catastrophic cycles and built structures designed to survive major disasters. The positioning of ancient monuments like the pyramids, Stonehenge, and Easter Island statues appears to follow specific geographic and astronomical criteria that would maximize their chances of surviving major geological events. These structures are built using construction techniques that can withstand massive earthquakes and are located in areas that geological analysis suggests would be relatively stable during catastrophic events. The mathematical precision and astronomical alignments of these monuments indicate their builders possessed sophisticated knowledge of planetary cycles and geological processes. Excavations at Göbekli Tepe in Turkey have revealed construction techniques and artistic sophistication that push back the timeline for advanced human civilization by thousands of years. The site contains massive stone pillars carved with complex reliefs and arranged according to precise astronomical alignments. Carbon dating indicates the site was built over 11,000 years ago, then deliberately buried under tons of soil around 10,000 years ago. The deliberate burial suggests the builders were preparing the site to survive a known catastrophic event. Similar patterns of intentional burial followed by later reconstruction appear at archaeological sites worldwide. Recent discoveries in Egypt have identified construction phases at the Giza pyramids that indicate they were built in multiple stages separated by long periods of abandonment. Ground-penetrating radar has revealed earlier structures beneath the current pyramids that show different construction techniques and orientations. The layered construction suggests that multiple civilizations built on the same sites after previous structures were damaged or buried by catastrophic events. Chemical analysis of the mortar used in different construction phases shows compositional differences that indicate the materials came from different time periods separated by thousands of years. Archaeological sites in the Americas show evidence of sophisticated engineering knowledge that was lost and rediscovered multiple times throughout history. The precision stonework at Pumapunku in Bolivia demonstrates cutting and fitting techniques that require advanced tools and mathematical knowledge. Yet the site shows signs of sudden abandonment followed by later attempts to rebuild using inferior techniques. This pattern of advanced construction followed by technological regression appears at sites throughout South America and suggests that advanced knowledge was repeatedly lost due to catastrophic events that disrupted civilizations. Chemical analysis of impact spherules found in sediment layers worldwide provides evidence of extraterrestrial impacts that coincide with catastrophic events. These microscopic glass beads form when asteroid or comet impacts vaporize rock and create atmospheric debris that rains down over large areas. The spherules contain high concentrations of iridium and other platinum group elements that are rare on Earth but common in asteroids. Dating of these spheral layers corresponds to the approximate times when archaeological evidence shows major civilizations disappeared and flood myths describe worldwide catastrophes. The mounting archaeological evidence of rapid burial events, sophisticated ancient construction, and cyclical destruction patterns has led researchers to examine the physical mechanisms that could produce such widespread catastrophic effects. Understanding how these ancient disasters actually occurred requires examining the fundamental forces that govern planetary stability. The mechanics of planetary catastrophe. Thomas's theory of crustal displacement operates on mechanical principles that mainstream geophysics rejects as physically implausible. He describes Earth's structure as consisting of a solid crust approximately 60 miles thick sitting on top of a thin molten zone, with deeper molten regions beneath that. However, no evidence supports the scenario where Earth's crust could slide rapidly over underlying layers like a loose peel. Modern understanding of crustal mechanics through seismic and core flow models demonstrates that the forces required for sudden crustal movement would exceed any known geological processes. The concept of rapid crustal displacement gained attention through Charles Hapgood's earlier work in the 1950s, which proposed that Earth's crust could shift position relatively quickly compared to normal geological timescales. Hapgood's theories received support from Albert Einstein, who wrote forewords for his books and engaged in correspondence about the mathematical possibilities of crustal movement. However, the development of plate tectonic theory in the 1960s provided a more comprehensive explanation for continental movement that operates through well-documented processes over millions of years rather than catastrophic shifts. Thomas expanded on Hapgood's foundation by incorporating magnetic field effects and rotational dynamics into his displacement mechanism. He theorized that the molten layers beneath Earth's crust could serve as lubricating zones that would facilitate rapid crustal movement under specific conditions. According to Thomas, the most significant triggering factor would be the uneven distribution of mass on Earth's surface, particularly the massive ice sheets that accumulate at polar regions during ice ages. The Antarctic ice sheet weighs approximately 24 million billion tons, while the Greenland ice sheet adds another 2.8 million billion tons concentrated at the polar regions. Thomas calculated that when ice accumulation reaches certain thresholds, the rotational forces acting on these off-center masses could overcome the friction holding the crust in place. The result would be the crust sliding toward the equator to re-establish rotational balance, carrying the continents to entirely new positions. This process would be accelerated by magnetic field disruption, as Earth's magnetic field helps stabilize the planet's rotational dynamics through electromagnetic forces generated by electric currents flowing through the molten iron in Earth's outer core. The catastrophic chain reaction process Thomas described involves multiple interconnected systems that would amplify the initial displacement. As the crust begins sliding, the atmosphere and oceans would continue rotating at their original speed while the land surfaces underneath change direction and speed. This creates relative motion between air masses and ground surfaces that generates winds of incredible velocity. Thomas calculated that atmospheric speeds could reach supersonic levels as air masses try to maintain their rotational momentum while the ground beneath them moves in different directions. Temperature extremes would develop rapidly during crustal displacement because the sun's position relative to Earth's surface would appear to change dramatically. Areas that were previously in temperate zones could suddenly find themselves in polar positions, experiencing rapid temperature drops that Thomas estimated could reach -80 degrees Fahrenheit. Conversely, polar regions that shifted toward the equator would experience extreme heating as they moved into tropical solar exposure. These temperature changes would happen over periods of hours or days rather than the gradual climate changes that occur over thousands of years. Modern geological understanding has moved beyond theories of rapid crustal displacement toward more precise models of how Earth's interior actually behaves. Seismic tomography and deep Earth monitoring reveal that the mantle and crustal interactions operate through convection processes that take millions of years to produce significant surface changes. The forces required to move entire crustal plates rapidly would need to overcome the enormous friction and structural integrity of rock formations that extend hundreds of kilometers into Earth's interior. Current geophysical models show that while Earth's magnetic field does influence some aspects of crustal behavior, the electromagnetic forces involved are insufficient to trigger the type of rapid displacement Thomas described. The magnetic field affects the flow of electrically conductive materials in the outer core. But these effects don't translate into forces capable of moving solid crustal plates quickly. The energy requirements for rapid crustal displacement would exceed any known geological processes by several orders of magnitude. Rotational dynamics do play a role in Earth's long-term geological evolution, but through processes that operate over much longer timescales than Thomas proposed. Changes in Earth's rotation axis, known as true polar wander, do occur as mass redistributes across the planet's surface. However, these changes happen gradually over thousands to millions of years as the planet adjusts to new mass distributions through normal geological processes. The physics of planetary rotation requires that significant axis changes occur slowly to maintain rotational stability. Despite the scientific consensus against rapid crustal displacement, Thomas's observations about the relationship between magnetic field behavior and geological activity contain elements that merit continued investigation. The correlation between magnetic field changes and increased seismic activity suggests that electromagnetic processes in Earth's interior do influence surface geological phenomena, even if not through the dramatic mechanisms Thomas proposed. The mounting evidence of magnetic field instability, combined with increasing geological activity worldwide, has prompted researchers to examine whether current planetary conditions might be approaching a threshold where significant changes become more likely. While these changes would occur through conventional geological processes rather than catastrophic crustal displacement, the patterns emerging in 2025 suggest that Earth's geological systems are entering 2025 seismic warning signs. Global seismic activity in 2025 has shown patterns that warrant scientific attention, though claims of extraordinary increases require careful examination. The United States Geological Survey data indicates that earthquake frequency remains within historical variability ranges, with 2023 seismicity rates showing normal fluctuations rather than dramatic increases. However, the distribution and characteristics of seismic events have developed some unusual patterns that researchers are monitoring closely. The Pacific Ring of Fire has experienced notable activity, with Japan recording significant earthquake sequences in the first half of 2025, though these fall within expected ranges for this seismically active region. Earthquake clustering patterns observed throughout 2025 show some alignment with geological stress indicators, though connections to catastrophic crustal displacement remain scientifically unsupported. Current seismic data reveals increased activity along certain fault systems, including extended earthquake swarms that persist longer than typical sequences. The San Andreas fault system has experienced earthquake swarms that continue for weeks instead of the usual few days, while similar extended activity appears along fault systems in Turkey, Chile, and New Zealand. However, these patterns reflect normal tectonic processes rather than precursors to planetary-scale crustal movement. Deep earthquakes occurring at depths between 300 and 700 kilometers have shown increased frequency since 2020, with 2025 recording notable deep seismic events. These deep earthquakes are significant because they indicate stress changes throughout the entire thickness of crustal plates rather than just surface-level adjustments. Normal tectonic activity produces most earthquakes at depths less than 100 kilometers, where brittle rock fractures along fault lines. The increase in deep earthquakes suggests that forces are acting on broader sections of the crustal system, though these forces operate through conventional geological processes rather than the rapid displacement mechanisms Thomas proposed. Volcanic activity has intensified in several key geological zones that correspond to areas of known crustal stress. The Yellowstone volcanic system has shown increased ground deformation and thermal activity, with new hydrothermal features appearing in areas that were previously stable. Similar changes are occurring at volcanic systems in Iceland, where ground uplift has accelerated and new fissures are opening at rates not seen since major eruptions in the 1700s. The Cascade Range in the Pacific Northwest has recorded increased seismic activity at depths that indicate magma movement beneath multiple volcanic peaks simultaneously. The connection between magnetic anomalies and seismic events has become increasingly apparent as both phenomena have developed together since 2019. Seismologists have documented correlations between earthquake frequency and regions where magnetic field strength is declining most rapidly. Areas experiencing rapid magnetic declination changes, such as the region around Hudson Bay in Canada, have subsequently shown increases in earthquake activity within months of the magnetic changes being detected. This correlation suggests that electromagnetic processes in Earth's interior may influence surface geological phenomena, though through conventional mechanisms rather than catastrophic displacement. Earthquake patterns throughout 2025 suggest crustal adjustments that reflect ongoing tectonic processes, rather than approaching catastrophic instability. Traditional plate tectonics produces earthquakes that follow predictable patterns based on the direction and speed of plate movement. Current earthquake distributions show some variations from standard tectonic models, with earthquakes occurring in locations that experience less frequent activity and some traditionally active areas showing periods of reduced seismicity. This redistribution of seismic stress indicates normal variations in tectonic forces rather than evidence of approaching crustal displacement. Modern seismic instruments have detected changes in deep Earth properties that provide insights into crustal behavior. Seismic tomography, which uses earthquake waves to image Earth's interior structure, shows variations in the boundaries between different layers beneath the crust in certain regions. These variations indicate that the physical properties of deep Earth materials undergo normal changes as part of ongoing geological processes. Temperature and pressure conditions at crustal interfaces fluctuate as part of the dynamic system that drives plate tectonics in volcanic activity. Accelerating geological changes observed through 2025 indicate that crustal systems are responding to ongoing tectonic forces through normal geological processes. The rate of seismic activity shows variations that fall within historical ranges, though the distribution patterns have shifted in some regions. These changes reflect the dynamic nature of Earth's crustal system as it continuously adjusts to internal forces and thermal variations. Similar patterns appear in historical geological data during periods of increased tectonic activity that occurred through conventional geological mechanisms. Timeline correlations between magnetic field changes and seismic activity show that earthquake patterns began showing variations approximately 18 months after magnetic pole acceleration became pronounced in 2019. This timing suggests that electromagnetic changes in Earth's core may influence crustal behavior through conventional geophysical processes. The correlation indicates that magnetic field variations and seismic activity are both responses to changes in Earth's interior dynamics rather than precursors to catastrophic events. Regional variations in seismic activity correspond to areas of known geological stress and tectonic activity. The North American continent shows earthquake activity concentrated along the western coast and through interior regions that experience ongoing tectonic forces. Similar patterns appear in Asia, where earthquake clusters follow established fault systems and areas of known crustal stress. These regional patterns reflect the normal operation of tectonic processes rather than building stress for catastrophic displacement. Scientific institutions worldwide have expanded their seismic monitoring networks in response to the need for better understanding of current geological activity. New seismometer installations focus on detecting deep earthquakes and monitoring regions that require additional data for comprehensive geological assessment. The expansion of monitoring capabilities reflects scientific interest in understanding current seismic patterns through conventional geological frameworks rather than preparation for catastrophic events. The seismic patterns observed in 2025, while notable for their regional variations and timing correlations with magnetic changes, operate within the bounds of normal geological processes. However, these geological adjustments are occurring alongside atmospheric changes that present their own concerning patterns. Climate chaos and atmospheric anomalies. Weather patterns recorded throughout 2025 show characteristics that meteorologists describe as unprecedented in recorded history. Temperature variations between different regions of the planet have reached extremes that don't follow seasonal patterns or gradual climate change trends. The Arctic has experienced temperature swings of over 40 degrees Fahrenheit within single weeks, while tropical regions have recorded heat indices that exceed normal measurement ranges. These temperature extremes appear suddenly and persist for weeks before shifting to equally extreme conditions in the opposite direction. Atmospheric circulation patterns have fundamentally changed from the stable systems that meteorologists used for weather prediction throughout the 20th century. The polar vortex has experienced disruptions in 2025 that sent cold air masses further south than typical patterns, though within documented ranges of Arctic outbreaks. NOAA data shows jet stream perturbations that create temperature inversions where some northern locations record higher temperatures than areas hundreds of miles closer to the equator. These circulation disruptions create feedback loops that amplify weather instability rather than allowing atmospheric systems to return to normal patterns. Jet stream behavior throughout 2025 demonstrates unprecedented undulations that meteorologists are working to understand through conventional atmospheric science. The jet streams, which are high-altitude air currents that normally flow in relatively stable west-to-east patterns, have developed extreme loops that persist for weeks instead of the few days that characterized normal jet stream variations in previous decades. The northern jet stream has created massive undulations that bring Arctic air into temperate regions while simultaneously pulling warm air into polar areas. These patterns correlate with known climate oscillations, including the Arctic Oscillation and El Niño Southern Oscillation effects, though their intensity exceeds historical ranges. The relationship between atmospheric changes and other planetary systems has become increasingly apparent as multiple phenomena have intensified together since 2019. Research teams studying these connections have documented that atmospheric disturbances follow some geographic patterns similar to regions experiencing magnetic field changes, though the mechanisms linking these phenomena remain subjects of ongoing scientific investigation. Current atmospheric disruptions operate through conventional meteorological processes rather than direct electromagnetic control of weather systems. Climate system changes are accelerating beyond the gradual warming trends that scientists previously documented through anthropogenic greenhouse gas forcing. The Intergovernmental Panel on Climate Change identifies human activities as the primary driver of current climate change, with greenhouse gas concentrations reaching levels that create enhanced warming effects. Ocean circulation patterns that typically change over decades are now showing variations within shorter timeframes. The Atlantic meridional overturning circulation has weakened significantly since 2000 and shows signs of continued decline. Similar changes are occurring in Pacific Ocean currents that normally provide climate stability for billions of people. Historical climate patterns preserved in ice cores and sediment layers show atmospheric conditions similar to current observations during previous periods of rapid environmental change. These paleoclimate records indicate that rapid atmospheric transitions occurred in coordination with other planetary changes throughout Earth's history. The atmospheric signatures include sudden temperature shifts, altered precipitation patterns, and atmospheric composition changes that provide context for understanding current observations. Ice cores from Greenland show that previous periods of rapid climate change involved atmospheric instability that intensified over periods of 10 to 20 years before reaching peak intensity. Environmental stability indicators that meteorologists use to assess long-term climate trends show accelerating changes throughout 2025. Atmospheric pressure patterns have become increasingly variable, with high and low pressure systems developing intensities that challenge weather prediction models. Storm systems are generating wind speeds and pressure gradients that exceed historical ranges for many regions. Hurricane and typhoon seasons have extended beyond their normal timeframes, with tropical storms forming in regions and seasons where they occurred less frequently historically. These storms are also maintaining strength at latitudes where they typically weaken, indicating that atmospheric energy distribution has changed. Extreme weather events in 2025 show clustering patterns that suggest they're responding to common underlying atmospheric forces rather than random climate variations. Heat waves, flooding, drought, and severe storms are occurring simultaneously across different continents in ways that indicate planetary-scale atmospheric disruption. The synchronization of extreme events matches computer models of atmospheric behavior during periods of rapid climate system change. These models predict that enhanced greenhouse forcing combined with natural climate variability would create atmospheric instability that generates coordinated weather extremes across multiple regions simultaneously. Regional climate zones are shifting at rates that represent significant departures from historical patterns. Areas that maintain consistent climate characteristics for decades are experiencing temperature and precipitation changes that represent transitions toward different climate classifications. Desert regions are receiving unusual rainfall while traditionally wet areas are experiencing severe droughts. These shifts represent rapid transitions between climate states rather than gradual adaptations to changing conditions. The speed of these transitions suggests that atmospheric systems are approaching critical threshold points where small changes trigger large-scale reorganization. Atmospheric monitoring networks have detected pressure wave patterns that propagate through the atmosphere in ways that require further scientific investigation. These waves appear to correlate with geological activity and create pressure disturbances that affect weather patterns across large regions. The waves show characteristics that suggest they may represent coupling between Earth's interior dynamics and atmospheric systems that becomes more pronounced during periods of increased geological activity. Atmospheric scientists working with current data confirm that 2025's weather patterns represent significant departures from historical norms, indicating that Earth's climate system is undergoing rapid changes through both anthropogenic forcing and natural variability. These atmospheric changes are occurring alongside mounting evidence that similar rapid environmental transitions have occurred multiple times throughout human history, leaving traces that researchers are only beginning to understand. The Lost Civilizations Connection. Archaeological discoveries from 2020 through 2025 have uncovered evidence that challenges established timelines of human civilization. Teams working with ground-penetrating radar have identified massive stone structures buried beneath sediment layers in locations where mainstream archaeology previously found no evidence of advanced societies. These discoveries include precision-cut megalithic blocks, sophisticated drainage systems, and architectural foundations that demonstrate engineering knowledge that appears earlier in human history than previously documented. The structures show construction techniques that require advanced mathematics, astronomy, and metallurgy to accomplish. Excavations at sites in Turkey, Peru, and Indonesia have revealed technological capabilities that suggest human advancement occurred earlier than conventional archaeological timelines indicate. At Göbekli Tepe, researchers continue finding evidence that the site required coordinated labor from thousands of workers using tools and techniques that represent sophisticated organizational capabilities for societies existing 12,000 years ago. The site's construction demonstrates planning and execution that required substantial social coordination and technical knowledge. However, mainstream archaeology attributes these achievements to known cultures rather than evidence of pre-Diluvian advanced civilizations. The construction techniques found at ancient sites demonstrate knowledge that goes beyond basic building skills documented for their respective time periods. Engineers analyzing megalithic walls at various ancient sites have identified construction methods that create earthquake-resistant structures capable of surviving seismic events that would damage conventional buildings. The stones are cut and fitted using interlocking techniques that allow walls to flex during ground movement without collapsing. Similar earthquake-resistant construction appears at ancient sites across different continents, suggesting that builders understood the need to create structures that could survive geological instability. Archaeological evidence indicates ancient builders possessed detailed knowledge of geological stability and catastrophic risk assessment. The positioning of major archaeological sites follows specific geographic criteria that correspond to areas identified by modern geological analysis as relatively stable during seismic events. Megalithic sites are often concentrated in regions that sit on stable continental platforms, away from major fault lines, and at elevations that would provide protection from flooding. This geographic distribution suggests the builders understood which locations would survive natural disasters and chose their construction sites based on geological stability criteria. Stone monuments and carved reliefs at ancient sites contain astronomical alignments that track celestial cycles with mathematical precision. The Sphinx and pyramids at Giza align with stellar configurations that correspond to precession cycles, while similar astronomical alignments appear at Stonehenge, Angkor Wat, and sites throughout the Americas. These alignments required sophisticated astronomical knowledge and suggest the builders were tracking celestial patterns they considered important for their civilizations. The mathematical precision needed to create these alignments indicates the builders possessed advanced understanding of orbital mechanics and long-term astronomical cycles. Carved symbols and artwork at megalithic sites contain representations that appear to document catastrophic events and survival strategies. Petroglyphs found at sites worldwide show symbols representing floods, geological movement, and astronomical events. The symbols appear across different continents in cultures that had limited known contact with each other, suggesting they represent shared knowledge about natural catastrophes. Some symbols show representations of the Earth experiencing dramatic changes, floods covering large areas, and groups of people seeking shelter in elevated locations. The consistency of these symbols indicates they may represent attempts to preserve knowledge about natural disaster cycles for future generations. Claims about multiple successive advanced civilizations with specific catastrophe-proof designs remain disputed within archaeological circles. While some researchers propose theories about lost civilizations like Atlantis, conclusive evidence for such societies remains elusive. The archaeological record shows evidence of sophisticated ancient cultures, but mainstream archaeology attributes these achievements to known historical societies rather than evidence of cyclical destruction and rebuilding by advanced Prediluvian civilizations. The interpretation of ancient sites as evidence of lost advanced civilizations requires assumptions that extend beyond current archaeological consensus. Underground installations discovered through ground-penetrating radar suggest ancient civilizations built extensive subterranean complexes that could provide protection during surface disasters. These installations show evidence of advanced planning and include features designed to support populations during extended periods of isolation from surface conditions. The complexes include ventilation systems, water supplies, and storage areas that demonstrate sophisticated engineering capabilities. However, mainstream archaeology dates these structures within established historical timelines rather than as evidence of prehistoric advanced civilizations. Archaeological sites show evidence of knowledge preservation systems designed to protect information through natural disasters. Stone chambers at various sites are constructed to protect interior spaces from floods, earthquakes, and other environmental threats while preserving carved information on interior walls. The chambers are built using materials and techniques that maintain structural integrity over extended periods. These preservation systems suggest ancient civilizations developed systematic approaches to protecting important cultural and technical knowledge through periods of environmental instability. Advanced manufacturing techniques found at ancient sites indicate technological capabilities that appear sporadically throughout the archaeological record. Archaeological evidence shows that ancient civilizations produced sophisticated tools and worked with materials that require advanced processing techniques. However, these capabilities appear at different times and locations in ways that suggest independent development rather than inheritance from previous advanced civilizations. The pattern of technological advancement shows normal cultural development rather than evidence of cyclical destruction and rebuilding. Construction projects at ancient sites show evidence of multiple building phases separated by periods of abandonment and reconstruction. Carbon dating reveals that major sites were built, abandoned, then rebuilt by later civilizations using different construction techniques. This pattern reflects normal cultural transitions, population movements, and technological development rather than evidence of catastrophic destruction followed by rebuilding. The rebuilding efforts show that later civilizations found and studied the remains of previous societies, incorporating useful knowledge into new construction projects. Archaeological evidence demonstrates that ancient civilizations possessed sophisticated knowledge and capabilities that challenge conventional timelines of human development. However, the interpretation of this evidence as proof of cyclical catastrophic destruction remains outside mainstream archaeological consensus. The mounting evidence of ancient sophistication raises questions about human technological development that researchers continue investigating through conventional archaeological methods. These questions become particularly relevant when considering how dependent modern civilization has become on technological systems that require stable environmental conditions to function properly. Modern technology's vulnerability. Critical infrastructure systems across the globe face unprecedented risks from the accelerating magnetic field changes documented throughout 2025. Our electrical power grids depend on stable magnetic conditions because transformers and transmission lines are sensitive to magnetic field fluctuations. When the magnetic field experiences rapid changes, it induces electrical currents in power lines that can overload transformers and cause widespread blackouts. The 1989 geomagnetic storm that knocked out power across Quebec for 9 hours demonstrates how magnetic disturbances can cripple electrical systems. However, magnetic pole reversals occur gradually over thousands of years according to paleomagnetic records, meaning power grids face risks from space weather events like solar storms rather than sudden magnetic field collapse. Satellite networks that provide communication, navigation, and internet services are extremely vulnerable to magnetic field disruption and space weather effects. Satellites operate outside Earth's protective atmosphere where they rely on the magnetic field to deflect harmful radiation from space. As the magnetic field weakens, Satellites experience increased radiation exposure that damages their electronic components and shortens their operational lifespans. The GPS satellite constellation has already required more frequent maintenance and replacement due to radiation damage from weakened magnetic protection. NASA research confirms that while magnetic reversals happen gradually, the weakening magnetic field during the transition period increases satellite vulnerability to solar particle events and cosmic radiation. Navigation systems used by aircraft, ships, and ground vehicles all rely on magnetic field measurements for accurate positioning. Airplane autopilot systems, marine compasses, and smartphone navigation apps require precise magnetic declination data to function correctly. As magnetic field changes accelerate, these systems are producing increasingly inaccurate readings that create safety hazards for transportation. Commercial aviation has already implemented new procedures requiring pilots to verify magnetic compass readings against GPS coordinates because magnetic navigation is becoming unreliable. The accelerating magnetic pole drift documented in 2025 means navigation systems require constant recalibration to maintain accuracy. Computer systems and electronic devices face potential failure during severe geomagnetic storms because they're designed to operate within specific electromagnetic parameters. The integrated circuits that power everything from smartphones to industrial control systems are sensitive to electromagnetic interference. Strong magnetic field fluctuations can induce electrical currents in electronic circuits that cause temporary malfunctions or permanent damage to sensitive components. Modern electronics lack the hardening necessary to survive severe electromagnetic effects, though the gradual nature of magnetic reversals provides time for technological adaptation. Banking and financial systems that rely on electronic transactions and digital records would face significant disruption during severe space weather events. Credit card systems, ATM networks, and stock market trading platforms all depend on satellite communications and computer networks that could fail during electromagnetic storms. The global economy operates on electronic transfers and digital record keeping that remain vulnerable to electromagnetic disruption. NOAA and FEMA have established protocols for geomagnetic storm preparedness that include backup systems for critical financial infrastructure. Food distribution systems in developed countries depend on complex logistics networks that coordinate transportation, refrigeration, and inventory management through electronic systems. Trucks delivering food to grocery stores rely on GPS navigation and electronic communication systems to operate efficiently. Refrigeration systems that preserve food during transport and storage require electrical power that could be disrupted by geomagnetic effects on power grids. Modern agriculture uses computerized equipment for planting, harvesting, and processing crops that would face challenges during severe electromagnetic events. Medical systems and hospitals operate life support equipment, diagnostic machines, and pharmaceutical manufacturing that all require stable electrical power and electromagnetic conditions. Patients dependent on electronic medical devices like pacemakers, insulin pumps, and dialysis machines would face serious risks during severe geomagnetic storms. Hospital backup generators and medical equipment aren't designed to handle intense electromagnetic interference. Emergency preparedness protocols now include provisions for protecting critical medical equipment during space weather events. Water treatment and sewage systems in urban areas rely on electric pumps, computerized monitoring, and automated control systems that could fail during electromagnetic disruption. Cities pump water from distant sources using electrical systems and treat sewage through processes that require constant electrical power. Urban populations that depend on these centralized systems would lose access to clean water and sanitation during extended power outages. Emergency management agencies have developed contingency plans for maintaining essential services during infrastructure disruptions. Transportation networks including air traffic control, railroad signaling, and highway management systems all depend on electronic communication and navigation that electromagnetic storms could disrupt. Air travel would face significant challenges without radar systems and electronic navigation aids that keep aircraft safely separated. Rail transportation relies on computerized signaling systems that prevent collisions and coordinate train movements across networks. Highway systems use electronic traffic control and emergency communication systems that remain vulnerable to electromagnetic effects. Manufacturing and industrial processes use computerized control systems, robotic assembly lines, and electronic monitoring that could shut down during severe geomagnetic events. Chemical plants, oil refineries, and nuclear power facilities require constant electronic monitoring and automated safety systems to operate safely. These industrial facilities have implemented backup systems and electromagnetic hardening measures for critical operations. The industrial infrastructure that supports modern civilization has developed resilience measures for space weather events. Government preparations for electromagnetic disruption include established NOAA and FEMA protocols for geomagnetic storm preparedness rather than classified extinction-level threat programs. Military installations have implemented electromagnetic hardening measures for essential communication and defense systems, while civilian infrastructure continues developing protective measures. Emergency management agencies have developed contingency plans for widespread power outages and communication failures based on documented space weather risks. Scientific institutions have studied the cascading failure effects that severe electromagnetic events could create across interconnected technological systems. Computer models show that failure of satellite communications could trigger failures in power grids, which would cause failures in water systems, transportation networks, and financial systems in sequence. The interdependence of modern technological systems means that failure of major components could cause failures throughout infrastructure networks. However, the gradual nature of magnetic reversals provides time for adaptation and system hardening. The mounting evidence of accelerating magnetic field changes, combined with increasing technological dependence, has prompted researchers to examine whether current conditions might indicate approaching critical thresholds. While electromagnetic risks operate through conventional space weather processes rather than catastrophic scenarios, the patterns emerging in 2025 suggest that understanding the timing of these changes has the timeline question. Determining when these planetary changes might reach critical levels requires examining the evidence Thomas compiled and comparing it to current observations. Thomas's original timeline calculations placed significant catastrophic events in Earth's past, though his claims about precise cyclical timing lack scientific foundation. While orbital and solar cycles do affect climate patterns over long periods, no evidence supports regular crustal displacement resets occurring on predictable schedules. Thomas connected his timeline to worldwide flood myths and geological evidence of rapid climate change, suggesting that catastrophic events followed patterns that could be used to predict future occurrences. He calculated that the next catastrophic pole shift would occur sometime in the early 21st century, with his predictions placing the probable time frame between 2000 and 2030. The most likely period, according to his analysis, would be the 2020s, when multiple planetary factors would align to create conditions he believed favorable for crustal displacement. Current observations from 2025 show some alignment with the warning signs Thomas predicted would appear in the decades preceding catastrophic events. He described a period of accelerating magnetic pole movement that would begin approximately 60 years before major events. Magnetic pole tracking data shows that significant acceleration began in the 1990s and has intensified dramatically since 2000. The exponential increase in pole movement speed observed since 2019 corresponds to what Thomas described as the final phase of magnetic instability. Though mainstream geophysics interprets these changes through conventional field evolution rather than precursors to catastrophic displacement. Mathematical models developed by researchers studying planetary risk assessment have created algorithms for evaluating catastrophic timing based on multiple variables including magnetic field behavior, seismic activity patterns, and climate indicators. However, mainstream geological consensus sees no imminent catastrophic displacement, with current meteorology and geophysics predicting normal field evolution rather than rapid breakdown within decades. The models show correlations between various planetary phenomena, but these correlations operate through conventional geological processes rather than the catastrophic mechanisms Thomas proposed. The acceleration rates observed in 2025 have prompted some researchers to examine whether critical threshold conditions might be approached sooner than conventional geological timescales suggest. Magnetic field decline has accelerated in certain regions, while magnetic pole movement shows continued acceleration patterns. If current trends continue, some researchers suggest that significant magnetic field changes could occur within decades rather than the thousands of years typical of geological processes. However, these projections remain within the bounds of normal magnetic field evolution rather than indicators of catastrophic crustal displacement. The convergence of multiple planetary phenomena has created what some researchers describe as a period of increased geological activity worthy of scientific attention. seismic activity patterns, magnetic field changes, atmospheric disruption, and climate instability are all showing variations from historical norms. Thomas described this convergence of warning signs as significant for understanding planetary behavior, though his specific predictions about catastrophic outcomes lack scientific support. The correlation between current observations and Thomas's general descriptions of planetary instability has surprised some researchers who initially dismissed his work entirely. Expert opinions on catastrophic probability vary significantly depending on whether researchers accept conventional geological frameworks or consider alternative theories about rapid planetary change. Geophysicists who study magnetic field behavior acknowledge that current changes represent unprecedented observations in the modern instrumental record, though most maintain that catastrophic crustal displacement remains physically implausible. Mainstream geological consensus emphasizes that current changes operate through normal geological processes that unfold over extended timescales rather than catastrophic events. Independent research teams studying geological risk assessment have developed mathematical models for evaluating planetary stability using current magnetic field data, seismic patterns, and climate indicators. While these teams operate within conventional geological frameworks, their models show correlations between various risk factors that peak during periods of increased geological activity. The mathematical relationships between different planetary phenomena suggest that understanding these correlations could provide insights into geological behavior, even without accepting catastrophic displacement theories. Warning sign patterns observed throughout 2025 show some correspondence to sequences Thomas described, though these patterns operate through conventional geological processes rather than precursors to catastrophic events. Magnetic anomalies have accelerated, seismic activity has shown regional variations, atmospheric patterns have demonstrated unusual characteristics, and climate indicators have displayed instability. The sequence of these phenomena matches some aspects of Thomas's descriptions, though mainstream science interprets these changes as normal variations in Earth's dynamic systems. Current data acceleration suggests that geological processes are operating at rates that compress some traditional timescales for planetary change. Previous magnetic field transitions occurred over thousands of years, but current changes are happening at rates that represent significant departures from historical patterns. The compression of these timescales means that understanding geological behavior requires examining processes that operate faster than conventional geological wisdom previously acknowledged, though still within the bounds of normal planetary evolution. Multiple calculation methods indicate that geological systems are approaching periods of increased activity that warrant scientific attention. Magnetic field projections, seismic stress models, and climate instability calculations suggest that various planetary systems are experiencing changes that represent departures from stable baseline conditions. The synchronization of these different indicators suggests that Earth's geological systems are entering a period of increased activity that deserves careful monitoring through conventional scientific methods. Scientific institutions have expanded monitoring programs based on the need to better understand current geological activity patterns. Government agencies responsible for disaster preparedness have developed contingency plans for scenarios involving infrastructure challenges from space weather events and natural disasters. These preparations reflect standard emergency management protocols rather than preparation for catastrophic planetary events. The practical measures being implemented represent normal disaster preparedness rather than responses to imminent catastrophic threats. Current conditions may represent a period of increased geological activity that provides opportunities to better understand how Earth's systems behave during periods of change. Thomas's observations about planetary behavior, while containing elements that lack scientific support, have prompted researchers to examine correlations between different geological phenomena more carefully. Whether current changes represent normal geological variation or indicators of more significant transitions remains an active area of scientific investigation. The evidence suggests that understanding these planetary changes has become important for assessing how current conditions might affect human civilization. While catastrophic scenarios remain outside mainstream scientific consensus, the patterns emerging in geological data indicate that preparation for various types of natural disasters and infrastructure challenges represents prudent planning for an uncertain future. Survival and preparation strategies. Developing effective preparation strategies requires moving beyond theoretical discussions toward practical measures that address realistic scenarios rather than speculative catastrophic events. Individual preparation for natural disasters and infrastructure challenges should focus on established emergency preparedness protocols rather than planetary-scale survival scenarios. Standard disaster preparedness assumes that emergency services will restore normal conditions within reasonable timeframes, which represents the most likely outcome for natural disasters, including severe space weather events, earthquakes, and extreme weather conditions. Geographic considerations for emergency preparedness involve understanding regional risks and developing location-specific preparation strategies. Areas prone to hurricanes require different preparation approaches than regions facing earthquake risks or severe winter weather. Coastal regions need evacuation plans for storm surge and flooding, while inland areas focus on power outages and supply chain disruptions. Mountain regions prepare for avalanches and isolation during severe weather, while desert areas plan for extreme heat and water scarcity. Understanding local hazards allows communities to develop targeted preparation strategies that address the most likely emergency scenarios they might face. Government emergency management programs provide frameworks for disaster preparedness that individuals and communities can build upon. FEMA guidelines establish baseline preparation recommendations including emergency supply kits, communication plans, and evacuation procedures. NOAA provides space weather alerts and preparedness guidance for geomagnetic storms that could affect power grids and satellite communications. State and local emergency management agencies develop region-specific plans that address local hazards and coordinate response efforts. These established programs represent tested approaches to disaster preparedness based on decades of emergency management experience. Emergency supply preparation should focus on maintaining resources for realistic disaster scenarios rather than long-term survival situations. Standard emergency kits include water storage for several days, non-perishable food supplies, battery-powered radios, flashlights, first aid supplies, and medications. Additional supplies for extended power outages include backup power sources, extra batteries, manual can openers, and warm clothing. Communication equipment including battery-powered or hand crank radios provides access to emergency information when normal communication systems fail. These supplies address the most common needs during natural disasters and infrastructure disruptions. Technology protection during electromagnetic events involves following established guidelines for space weather preparedness rather than extensive hardening measures. NOAA recommendations include unplugging sensitive electronic devices during severe geomagnetic storms, maintaining backup power sources for essential equipment, and having alternative communication methods available. Simple protective measures like surge protectors and battery backup systems provide adequate protection for most space weather events. More extensive protection measures are typically unnecessary for civilian applications, as severe electromagnetic events remain relatively rare and usually affect specific geographic regions rather than global infrastructure. Community preparedness initiatives create networks of mutual support that enhance individual preparation efforts. Neighborhood emergency response teams coordinate local disaster response and provide assistance to vulnerable community members. Community gardens and local food production systems increase food security during supply chain disruptions. Local communication networks using amateur radio operators maintain contact between communities during infrastructure failures. Skill-sharing programs teach practical capabilities including basic medical care, food preservation, and equipment repair that prove valuable during emergencies. Realistic emergency scenarios focus on infrastructure challenges that communities actually face during natural disasters. Power outages lasting days or weeks require backup heating, lighting, and food preservation methods. Water system failures need alternative water sources and purification methods. Communication disruptions require backup methods for contacting family members and receiving emergency information. Transportation limitations during severe weather or infrastructure damage need alternative travel plans and supply storage. Medical emergencies during infrastructure failures require basic first aid capabilities and medication storage. Historical examples of disaster recovery provide guidance for effective preparation strategies. Communities that maintain strong social networks recovered faster from natural disasters than those with limited community connections. Regions with diversified local economies showed greater resilience during extended infrastructure disruptions. Areas with established emergency communication systems coordinated response efforts more effectively during crisis periods. Communities that practiced emergency procedures regularly responded more efficiently when actual disasters occurred. These historical patterns inform current emergency preparedness recommendations. Knowledge preservation during emergencies involves maintaining access to essential information when normal communication systems fail. Physical copies of important documents including identification, insurance policies, and medical records should be stored in waterproof containers. Emergency contact information and evacuation routes should be available in multiple formats, including written copies that don't require electronic devices. Basic reference materials including first aid guides, local maps, and emergency procedures provide essential information during infrastructure failures. Educational materials about local hazards and emergency procedures help community members respond effectively during crisis situations. Resource management during extended emergencies requires careful planning for supply conservation and allocation. Water storage and purification methods extend available supplies during infrastructure failures. Food preservation techniques including canning, drying, and root cellars maintain nutrition when supply chains are disrupted. Fuel conservation strategies reduce dependence on external energy sources during power outages. Medical supply management ensures essential medications remain available during extended emergencies. These resource management techniques address realistic scenarios where communities might face weeks or months of limited access to normal supply chains. International cooperation in disaster preparedness involves sharing best practices and coordinating response capabilities across different regions. Emergency management agencies exchange information about effective preparation strategies and response techniques. Scientific institutions collaborate on monitoring systems that provide early warning for natural disasters and space weather events. International aid organizations coordinate relief efforts and resource sharing during major disasters. These cooperative efforts enhance global disaster preparedness capabilities and provide support networks for communities facing major emergencies. The evidence examined throughout this analysis reveals patterns that suggest preparation for various natural disasters and infrastructure challenges represents essential planning for modern communities. Whether these patterns indicate normal geological variation or something more significant, the practical steps for emergency preparedness remain fundamentally the same, focusing on realistic scenarios that communities can effectively address through established emergency management principles. The accumulating data from 2025 provides a clearer picture of what's actually happening to our planet. Current observations show magnetic pole drift acceleration to approximately 40 kilometers per year, moderate field weakening of about 9% over the last 200 years, and seismic activity that remains within normal statistical variability. While these changes represent notable departures from historical patterns, they operate through conventional geological processes rather than the catastrophic mechanisms Thomas proposed. Thomas's theory about cyclical crustal displacement remains speculative, lacking the scientific evidence required for mainstream acceptance. However, the correlations he identified between magnetic field behavior, geological activity, and climate patterns deserve continued scientific attention. Current monitoring programs by NOAA, NASA, and international research institutions provide unprecedented data about how Earth's magnetic and geological systems actually behave during periods of change. Is rapid pole shift possible? Current science indicates that magnetic field changes occur gradually over thousands of years, allowing time for technological adaptation rather than requiring immediate survival preparations. The most productive approach involves staying informed through real-time data from established scientific institutions rather than preparing for speculative catastrophic scenarios. What surprised you most about the confirmed scientific facts we've covered? Share your thoughts in the comments about which verified observations,